Assalamualaikum and good afternoon everyone. We are from Group 4. We'll present to you guys what we observed during the field trip. First of all, I'll introduce to you guys our group members. First, Nur Ain. Second, Nur Amira, Nur Atira, Siti Aisyah, Nur Hidayah, Nur Shamimi, Nur Farisha, Nur Izzati and Nur Atira. Okay, we start with pattern 1. Location, Mardi Cerating Pahang. And the series for pattern 1 is Siri Baging. The coordinate, you guys can see on the slide. And elevation, 3 meter from the sea level. Land use is agriculture. Drainage class 9 and the parent material for pattern 1 is marine sand, and the slope values are 5 degree, 2 degree and 1 degree. Okay, next I will go through the factors of soil formation and the processes. First factor is parent material. Parent material for pattern 1 is marine sand. Marine sand can cause the formation of soil in a few ways. One of them is composition. Marine sand is primarily composed of small rock and mineral particles that have been eroded and transported by water, often from marine environment. The composition of marine sand can vary depending on the sources, but it typically contains minerals such as quartz, feldspar, and mica. Secondly, soil formation, also known as pathogenesis, involves the weathering and transformation of the parent material into soil. Marine sand may undergo weathering process like chemical weathering and physical weathering, leading to the development of soil horizons. Lastly, limitation. Sandy soil tend to have lower water and nutrient retention capacity compared to soil with finer texture like clay or loam. The next factor is slope. Here are some ways in which the slope of sandy soil can cause formation of soil. First, profile development. The angle of the slope can impact the soil profile development. On the steeper slopes, the soil profile might be shallower due to increased erosion, while on gentler slope, soil horizon might be more well developed. Second, slope stability. Erosion on steep slope can lead to the disappear of topsoil. However, gentler slope may retain more soil, allowing organic matter and minerals to accumulate. The slope stability can influence the long-term development of a soil profile. Next is erosion and deposition. On sloping ground, gravity can cause erosion of sandy particles. Water flow from higher layer can move sand to down layer. However, when the slope reduces, water velocity may slow, allowing for sand accumulation. This process may lead to the production of various soil layer and profile. Lastly, water circulation. Slope affect water movement through the soil. On steep slope, water runoff is more rapid, potentially leading to reduced water retention in the soil. This can influence the type and depth of soil development as well as the leaching of minerals. Next factors is leaching. Leaching in soil can lead to formation of soil in many ways. One of them is by removal of soluble material. Because sandy soil are porous, water may travel through them more quickly. As water penetrates the soil, it can dissolve and transport soluble elements like minerals, ions, and nutrients. This leaching process might result in the removal of chemical from the upper soil horizon. Lastly, mineral weathering. Leaching can help minerals weather in soil. When water interacts with mineral particles, chemical reaction can occur, causing mineral to break down into secondary compounds. This process is part of the larger soil formation process known as pathogenesis.
The next factor is plant. For your information, root produce carbon dioxide that mix with water and form an acid that whirl over rock. As you can see in Madrigeratin, there are many roots that arise when we dig the ground. This indicates that the soil is fertilized because plant roots penetrate the soil, breaking it up physically and contributing to mechanical weathering. Organic matter produced by plants such as fallen leaves and decaying roots enrich the soil with nutrients and increase its fertility. The next factor of soil formation is oxidation. In oxidation, oxygen from the air reacts with iron in rock to form iron oxide. This reaction creates a rusty brown coloration on rock. Oxidation is a process that can contribute to the darkening of soil, especially in the surface layer. As you can see in Madrigeratin, the color of the soil generally becomes lighter as you move deeper into the soil profile due to reduced oxygen ability and reduced oxidation process. Next is temperature. Temperature affects chemical and biological process in soil formation. Temperature can also influence the rate of decomposition of organic matter, which is a vital component of soil formation. The average temperature in Karating in December for a typical day range from a high of 82 Fahrenheit, which is 28 Celsius, to a low of 77 Fahrenheit, which is 25 Celsius. The last factor of soil formation is rainfall. For your information, water is a major agent of weathering, and weathering is a big player in soil formation. Rainwater, which is slightly acidic due to the presence of dissolved carbon dioxide, can react with mineral, causing them to break down and release ion. So this watering process can break rock into smaller fragments, a crucial step in soil formation. At Mediterranean, the ground was moist because it has just rained last night.
Okay, now let's move on to pedantry. Our location right now is in Teluk Cepedak. The series is Renggam. First, the coordinate. As you can see, the value is on the slide. Secondly is elevation, which is 9 meters from the sea level. For the land use, it was secondary forest. The drainage is class A. The paramaterial is granite. And lastly, the value of slope is 20 degree, 10 degree, and 9 degree.
Next, I will present what the factors of formation soil for Pedant 2 and the processes. In the term parent material for Pedant 2 is granite. Granite as parent material can influence the formation of soil in many ways. Firstly, by mineral weathering. Granite is made up of minerals like feldspar which weathers chemically when exposed to the elements. The weathering process causes minerals to break down into smaller particles such as clay, silt, and sand. Granite weathering helps to produce soil over time. Second way is formation of soil layer. As granite weathers, soil horizon form. The top layers, known as the A horizon or topsoil, can store organic matter and nutrients produced from degraded plant material. The process of mineral leaching and transpiration can help to build lower horizons such as the B horizon or subsoil, which lead material accumulation, and the C horizon, parent material from which the soil forms. Next factor is slope. Sandy clay soil are characterized by a mixture of sand and clay particles, and the slope can impact soil development in a few ways. First, erosion. On steep slopes, water runoff can cause erosion by carrying away finer clay particles while leaving coarser sand particles behind. Sedimentation can occur in low-lying places or near the slope's base, causing eroded material to be deposited. This method can help to generate soil layer with different texture. Secondly, drainage characteristic. Sandy clay soil, water retention and drainage properties are influenced by their slope. Water may run off faster on steeper slope, resulting in less water retention in the higher layers. On gentler slope, however, water retention may be higher, affecting moisture distribution and soil growth. Next, leaching. First, water percolation. Water percolating through sandy clay soil may cause leaching, in which soluble nutrients pass down through the soil profile. The downward flow of leach material can help to form discrete soil horizon with different nutrient contents. Next, formation of layers. Leaching contributes in the formation of several soil layers, especially the alluviation E horizon. The E horizon is distinguished by mineral leaching and removal, by which in a light colored layer.
For the next factor, for soil formation, which is plant, we can see in this picture there are also roots that come up when we dig the soil. But the roots are not many and big like in Madicerating. In Teluk Cepedak, there are more big and thick trees than in Madicerating because it is close to the beach, while the place we dug in Teluk Cepedak is close to the forest. Next is oxidation. In Teluk Cepedak, the color of the soil generally become lighter as you move deeper into the soil profile due to reduced oxygen availability. At the Teluk Cepedak, the soil at the top is dark, but the deeper it goes, the soil become brown and more orange. Overall, the orange color in the deeper soil layer often indicate the accumulation of iron oxide, especially hematite in the soil profile.
For the temperature in Teluk Cepedak, the weather in Teluk Cepedak in December is very warm, humid but cool, with average high of 83 Fahrenheit, which is 28 Celsius, and low of 74 Fahrenheit, which is 23 Celsius. For the last process of formation of soil, which is rainfall, the ground condition in Teluk Cepedak is moist and a little wet because the rainy season. So we can see the condition of the ground. When it rains, the soil there is quite dark compared to the near Madicerating.
Development and morphology of soil. For Pedant 1 at Madicerating have 7 horizons. Firstly, O, organic horizon, depth 0 to 16 cm, the color dark grey. A refer to topsoil. A1 16 to 23.5 cm, the color dark grey. A2 23.5 until 34 cm, the color grey. B refer to subsoil. B1 34 until 51 cm, B2 51 until 79 cm, B3 79 until 93 cm, and the last B4 93 until 100 centimeter. From B1 until B4, the color is yellowish brown. Next, soil identification and mineralogy. First, sand. Dominant mineral is usually quartz. Second, silt, composed of various mineral like quartz, feldspar. Formed through weathering minerals like feldspar. 3. Other minerals may include mica, magnetite, and various heavy minerals. And last, marine sands can also contain organic materials, shell fragments, and debris from marine organisms, adding to the complexity of their composition.
Now I will present the development and morphology of soil, which is the soil profile of this padum. This is the horizon that we have identified at the field. We have O horizon at the top, contents of organic material, followed by A horizon. Then we have B1, B2, B3, B4, and B5 horizon. The depth represents each horizon's thickness. Each horizon have its own color as I showed in this table. For soil identification and mineralogy, this soil has a balanced mixture of sand, silt, and clay. For sand, primarily composed of minerals such as quartz. In silt, it is composed of various minerals such as quartz and feldspar. In clay, it is composed of clay minerals such as kaolinite, montmorillonite, and illite. It is also formed through weathering minerals like feldspar.
So now, I will explain the properties of soil for Padum 1. The soil was divided into 7 layers. The texture of the first to third layers is loam. From the picture, we can see plant roots can reach the third layer. Loam provides a favorable environment for plant roots to penetrate and access nutrients and water. And they are also fertile, easy to work with, and provide good drainage. The fourth layer seventh layer are sandy loams. The texture of sandy loam is moderately coarse due to the highest sand content. Sandy loam soil has excellent drainage properties due to the highest sand content. Water drains relatively quickly, preventing waterlogging and providing aeration for the plant roots, but for the particle size from the first layer to the seventh layer, it is generally 0.002 mm to 4.75 mm, and we can see that as fine grained because basically the soil at Mardi is a sandy soil. So now I will explain the structure, bulk density, and the color of soil. For the first soil profile, the structure are granular structure, loose and roots from overlying extend into the horizon. And the bulk density rich organic material, the color is dark gray. Second soil profile, the structure granular or crumb-like structure and irregularly shaped. The bulk density 0.8 grams over centimeter cube to 1.4 gram over centimeter cube, and the color is dark gray. Third, granular aggregates are small and rounded structures. The bulk density 1.0 gram over centimeter cube to 1.4 gram over centimeter cube, and the color gray. Fourth, the structure are angular blocky and block-like pads, and the bulk density 1.2 gram over centimeter cube to 1.6 gram over centimeter cube, and the color is yellowish brown. Fifth, the structure weak, medium, leggy structure and pads have smooth surfaces, finely formed and brittle. The bulk density 1.3 gram over centimeter cube to 1.7 gram over centimeter cube, and the color is yellowish brown. Sixth, column-like pads without rounded caps and prismatic structure. The bulk density 1.4 gram over centimeter cube to 1.8 gram over centimeter cube, and the color is yellowish brown. 7. The structure are structureless loose sand mixed with clay and single grain, no distinct bed. And the bulk density 1.5 gram over centimeter cube to 1.9 gram over centimeter cube, and the color is light yellowish brown.
Next, I would like to talk about the properties of soil of Padum 3. As you can see on the slide, our group found that the soil profile 1 to 7 shows that the soil has fine-grained particles. Then, let's see one by one, where our group found that the soil texture for soil profile 1 is organic matter and has an unstructured organic little layer. Next, soil profile 2 to 5 are long but have a different structure, where soil profile 2 has weak fine granular structure. Beds are finely formed and extremely weak consistency. Soil profile 3 has structurally single grain, no distinct beds and loose sand grains with very fine clay. Soil profile 4 has moderate medium subangular blocky, beds are well formed and firm consistency, and soil profile 5 has moderate medium blocky structure, beds have rough surfaces and porous with variable consistency. While for soil profile 6 and 7 are sandy loam with different structures, which is for the soil profile 6 has weak medium blocky structure, pads have smooth surfaces, friendly form and brittle. Last but not least, for the soil profile 7 has structure is loose and mixed with clay single grain and no distinct pad. Next, let's look at the bulk density that we obtain where soil profile 1 is organic matter rich, then for profile 2 is ideal root crop range, soil profile 3 slightly compact or dense, 4 is indicated moderately compact, 5 is moderately compact, 6 is closer to levels that are considered compact or dense, and soil profile 7 is compact restrictive layer. Then next, look at the color part that our group obtained. The color for soil profile 1 is 3 per 2 with grayish brown. Soil profile 2, 4 per 3 brown. 3, 4 per 4 yellowish brown. For 4, 3 per 4 yellowish brown. 5, 4 per 4 yellowish brown. 6, 5 per 8 yellowish brown. And for 7 is 6 per 6 brown.
For the next slide, we will talk about the existing soil degradations and conservations. Soil degradation refers to the decline in soil quality or productivity, often as a result of human activities or natural processes. There are several types of soil degradation, each with its own causes and consequences. Some of the common forms of soil degradation include erosion and chemical pollution. First, erosion occurs when wind, water, or ice removes the topsoil, carrying away essential nutrients. This is the consequences were reduced soil fertility, loss of organic matter, and increased vulnerability to drought. Second is chemical pollution. The excessive use of agrochemicals such as fertilizers and pesticides can negatively impact soil health, and the consequences are soil pollution, loss of beneficial microorganisms, and potential harm to human health. For the conservations, we have terrace and cover crops. Terraces and cover crops are two important soil conservation practices that contribute to sustainable agriculture and help prevent soil degradation. Terracing involves creating level areas on sloping terrain to slow down water runoff, prevent soil erosion, and enhance water infiltration. Terraces are typically constructed in a series of steps along the contour line of the land. Terraces break the flow of water, reducing its velocity and minimizing soil erosion on sloping landscape. In addition to prevent soil erosion, terraces can help stabilize steep slopes and reduce the risk of landslide. Lastly, cover crops. Cover crops are crops grown not for harvest, but to cover and protect the soil during periods when the main cash crops are not actively growing. These crops are typically grown in between regular crop cycles. Cover crops provide ground cover, reducing the impact of raindrops and preventing soil erosion. The examples of cover crops are legumes, such as clover, peas, or veg, which fix nitrogen in the soil. Second, grasses, such as rye, oats, or barley, which provide good ground cover. And the third is brassicas, such as radishes or mustard, which can help break up compact soil. Both terracing and cover cropping are valuable tools in sustainable agriculture, helping to protect soil resources, improve fertility, and promote long-term environmental health. Based on Pattern 1 and 3, erosion and chemical pollution may incur, but not too much and still under control, because Pattern 1 has took care by Mardi and Pattern 3 just naturally happened.
As for agricultural suitability, texture, depending on their size, they can be classified as sand, silt, or clay. The relative proportion of sand, silt, and clay in the soil is known as soil texture. Sand particles range from 0.05 to 2.00 millimeters in diameter. Silt particles range from 0.002 to 0.050 millimeters, while clay particles are smaller than 0.002 millimeters. So how do we determine the soil texture? Through three methods: the laboratory method, texture by feel, and jar method. The method we are using are texture by feel. This method usually more of an estimation of the percentages of the separates based on feeling of a moist soil with the fingers. Though organic matter is not removed with the feel method and could influence the feel of sandy textures. So these are the types of sand and their textures. As you can see, there are silt, clay, loam, and sand. Silt feels smooth when moist and has a flowery appearance when dry. It changes shape easily and breaks apart with slight pressure. As for clay, it feels sticky and is bendable when moist, forms a ball easily and resists breaking even when pressed. Loam feels somewhat gritty, yet is easy to work. It holds its shape if formed into a ball when moist, yet still breaks apart easily when squeezed. Lastly is sand. Sand feels gritty when rubbed between your fingers, but it falls apart easily if formed into a ball and dropped from hand to hand. Next, agricultural suitability is the organic matter. Active organic matter provides habitat and food for beneficial soil organisms that help build soil structure and porosity, provide nutrients to plants, and improve the water holding capacity of the soil. Adding organic matter does not change the texture of soil, but it does change the physical properties related to the texture. Organic matter will help improve the structure in a heavy clay texture or a loose sandy texture. Why organic matter is important in soil? Organic matter significantly improves the soil's capacity to store and supply essential nutrients such as nitrogen, phosphorus, potassium, calcium and magnesium, and to retain toxic elements. It also allows the soil to cope with changes in soil acidity and also helps soil minerals to decompose faster.
Cation exchange capacity. Cation exchange capacity is an indicator of soil fertility as it shows the soil's ability to supply three important nutrients of plant which are calcium, magnesium and potassium. The function of CAC is to measure the ability of soil to hold cations by electrical attraction. CAC is held by negatively charged particles of clay and organic matter. The CAC of soils is influenced by several factors and one of them is pH. So pH is important for CAC. pH affects the charge on the soil particles, particularly the clay and organic matter components. At different pH levels, the exchange sites on these particles can be either positively or negatively charged. In acidic soils, which in lower pH values, the exchange site tends to be occupied by hydrogen ions, resulting in a net positive charge. On the other hand, at higher pH levels, which is in alkaline or basic soils, the exchange sites can become negatively charged, attracting and retaining cations more effectively. There are three levels of CAC. First, low CAC. Low CAC is typically below 10 milliequivalents per 100 grams of soils. Soils with low CAC may have poor nutrient holding capacity. Second one is medium CAC. It is generally range from 10 to 20 milliequivalents per 100 gram. Soils with medium CAC can hold a moderate amount of nutrients and are considered reasonably fertile. And the third one is high CAC. High CAC is typically above 20 milliequivalent per 100 gram. Soils with high CAC have a higher capacity to retain and exchange cations. Water retention. What is the meaning of water retention? It is the ability of soil to hold water. It is the capacity of soil to retain and store water that is available for plant uptake. Water retention is influenced by several factors including soil texture, organic matter content, and soil structure. Aeration. On the other hand, aeration of soil can be referred as the ability of soil to exchange gases, primarily oxygen and carbon dioxide, with the atmosphere. Adequate soil aeration is crucial for the growth and development of plant roots, as well as for the activity of beneficial soil organisms. Soil aeration is influenced by factors such as soil compaction, porosity, and the presence of organic material. Poor soil structure or high clay content can also limit aeration, decreasing pore spaces and restricting gas exchange. How soil texture plays a significant role in water retention. Soil texture plays a significant role in water retention. Each of these soils, namely sand, silt, and clay, has a unique characteristic that influence water retention in the soil. First, sandy soil. Sandy soil has larger particles. The coarse texture of sandy soil leads to larger pore spaces between the particles, allowing water to drain quickly through the soil. As a result, sandy soils have low water holding capacity and tend to dry out faster. Second is silt soil. Silt soil is composed of medium-sized particles that are smaller than sand but larger than clay particles. It has smaller pore spaces compared to sandy soil. This finer texture enhances the soil's water holding capacity. Silt soil typically has moderate water retention capacity and moderate drainage. And the third one is clay soil. Clay soil has the finest texture and the smallest particles. Due to its small particle size, clay soil has very small pore spaces, resulting in poor drainage. Clay soils also have excellent water holding capacity as they can retain substantial amounts of water within their particles. Soil nutrient sufficiency. What is the meaning of soil nutrient sufficiency? Soil nutrient sufficiency is the availability and balance of essential nutrients in the soil that are necessary for optimal plant growth and development. How can we determine if a soil has sufficient nutrients? To determine soil nutrient sufficiency, various methods can be employed. Soil testing is a common practice where samples are taken from a representative area and analyzed for nutrient content. This analysis can provide information about the levels of different nutrients present in the soil, allowing farmers and gardeners to assess their sufficiency. Soils with balanced nutrient levels are considered suitable for agriculture, while imbalanced nutrient can negatively impact plant growth and productivity. So here is some practices to help maintain soil nutrients. First, by planting cover crops such as legumes or grasses, which can help prevent soil erosion, improve soil structure and fix nitrogen, which increase available nutrients for subsequent crops. Then adding organic matter such as compost, animal manure or crop residues to slowly release nutrients and improve soil structure and nutrient holding capacity. Next, develop a nutrient management plan that accounts for the specific nutrient needs of different crops and fields. This plan should consider soil testing, crop rotation, fertilization strategies, and other sustainable practices to optimize nutrient availability while minimizing environmental impacts. Also, practice proper irrigation such as efficient watering systems and avoiding over-irrigation, which help to prevent nutrient leaching and promote optimal nutrient uptake by crops. Last but not least, utilize organic and natural fertilizers as these products can contribute to soil fertility while minimizing the use of synthetic chemicals.
That's the end of our presentation. Thank you for your attention and have a good day, everyone.